The function is both concave up and concave down, depending on where you're looking at it from. Certain things go from 2 dimensions to 3 dimensions to moving 4-dimensional, like moving blobs. It's a direct translation in this case. It's a direct translation. So all this is right here, this right here is the derivative of a function with respect to u, but there are 3 inputs. Nothing changes. The math is exactly the same as it was when we were dealing with input being x and y. Nothing changes. Visually, it looks a little more interesting. So instead of like a surface that's static, we're talking about like a sphere that's getting bigger, or like a cylinder that's getting bigger, or some amorphous like liquid thing that's getting bigger. But the math, the vector calculus, stays exactly the same. The gradient vector, you just add another term. The directional derivative, you just add another term. Nothing changes. We could try to find the directional derivative of this function at this point in this direction. So how would we go about doing that if we wanted to do that? What should we do first? What would it be nice to write down all of?
The unit vector.
Well, okay, we could do the unit vector first, sure, if you wanted to. So, yeah, either one. Now, one thing that I've noticed, make sure you just actually write down your partial derivatives and then evaluate them. You'll get really comfortable with these, and I hope you are. The challenge is that when you start doing all the comfortable things at the same time, you tend to do simple differentiation errors or commit simple differentiation errors. So literally, if f of x, xyz is xy plus z, what's f of xyz going to be?
What?
F of xyz is going to be what? It's going to be y. Never mind, right? What's f of y xyz going to be? X. And what's f of z xyz going to be? It's going to be just 1. Exactly right. So now what point are we plugging in?
-1, 0.
We're plugging -1, 0, 1 into each of these. So when you plug that in, what do you end up with here? 0. What do you end up with here? What do you end up with here? Oh wait, it's uno. Right. So now do we have the partials at each, the 3 partials for the gradient? Yes, we do. The thing that Matt brought up. So we know that v, the direction we're going in, what is it? It's 2I plus k equals, oh, sorry. Now what's actually, sorry, I don't know why it does this sometimes.
We even have to care about z.
It's there, but what is the magnitude of that piece? Yeah, so v in this case, it tells us v is 2I plus k.
J.
But what's in there?
0j.
Plus 0j. Like j is there, it's just 0. That's the direction you're going in. You need 3 here.
We need the upper of the...
Yeah, just put it in there, and then yes, things will collapse. The point is just don't overly collapse things when you don't need to. So anyway, so we need to unitize this thing, which again, I'm still using that. I don't know why. What's the unit vector going to be on this one? 2 over what? I plus 0j plus what? 1 over k, like this, right? So now how do you go about finding, so you have this information, how do you go about finding the actual the FU here? Oh, wow, that sounds worse. Yeah, we're using this right here. That's the directional derivative. So have we found all of these components?
Yeah.
Yeah, we found it. So we now know that f in the u direction, the directional derivative is going to be what? 0 times what? 0 times what?
0 times.
What is u1 in this case?
Oh.
Thank you. I'm doing it in overly complete fashion, okay? Plus, what's fy? -1 times what?
0.
Times 0, right? Plus what?
1.
Plus 1 times what? Root 5. Exactly. Now, do a lot of these zeros go away? Yeah. They're gonna nuke a lot of stuff, so we end up with 1 over root 5. Is it really easy to make a simple mistake in all of this?
Yeah.
Super easy.
It's just like 2D. It's just...
So if f is differentiable at ABC and u is a unit vector, then fu, nice, equals the gradient dot the unit vector, right? Here are the simple facts. The gradient in the direction of, in addition, the gradient, if it doesn't equal 0, then the gradient is in the direction of the greatest rate of increase of f. The gradient of f is perpendicular to the level surface, and the magnitude of the gradient is the maximum rate of change. These are things we talked about yesterday. These are literally the same things we talked about yesterday, except we're now adding a dimension. That's it. So other question is going to be 2 times
x minus 1.
x minus 1, if I could write it correctly, right? plus what?
4y minus 2.
2 plus
6z minus 3.
6 minus 3 equals
0.
0. Now, could we divide everything by 2?
Yeah.
Sure, if you wanted to simplify this, you can make it x minus 1 plus 2 times y minus 2 plus 3 times... Yeah, and could you rearrange this if you wanted to? Yeah, sure. You could, if you wanted to, x minus 1 plus 2y minus 4 plus what? 3z minus 9 equals 0. So then what do you end up with? X plus 2y plus equals what? 14. Boom. Done.